In this video, you will learn how to simulate a single-stage cold forging process using the isothermal analysis module of AFDEX 3D, the Intelligent Metal Forming Simulator. Let's get started with the process type first. Since the geometries of the workpiece and the dies are symmetric, we will carry out a 3D simulation of a 30-degree sector of the component. The temperature change will not be considered in this simulation. The information about the material is given on the left side. The dimensions of the workpiece are as shown in the figure on the left. The material of the workpiece is a steel grade and its initial temperature is that of room temperature. The final configurations of each stage of the dies are as shown in the picture. The dimensions indicated in the picture denote the distances between the control points at the final stroke of individual stages. Bondizing process is used to lubricate the workpiece in this forging process. Therefore, a corresponding friction formulation will be selected. A constant velocity condition will be used in the simulation because the material is rate independent. The upper die will move downward with a constant velocity of 1 mm per second and the lower die will remain stationary. The problem definition is complete. The result of the simulation would be a forged component as can be seen on the right side. So now, let's see how we can simulate this process using AFDEX. Double-click on AFDEX icon to execute AFDEX in your computer. Click on New to define a new process. In this process information window we will clearly define the process type. This is 3D cold forging process. So we will make the selections accordingly. Select cold forming and 3D simulation. We select Newton as the unit of force. So the unit of stress will be megapascal. This will be a flow analysis, which means only the mechanical effects of deformation of the workpiece will be considered in the simulation. Select rigid plastic deformation type. This means the elastic component of deformation is neglected in the simulation as it is insignificant. Since this process does not have any flash, select regular type under flash. Click OK. This is the main window of AFDEX. We will use the toolbar to set up the simulation step by step. First step is to import the geometry. Click on Model, from File and then select the geometry files in STL format. You must select the geometry files of the workpiece and the dies for all stages. Click Open. Note that you can get this geometry file inside your AFDEX installation folder. Let's move on to the second step, which is to define the material property. Click on Material, from Library and then select the steel grade AISI_1010, T equals 20 degrees Celsius, and then click Load. This will load the material into the simulation. Now click Close. The third step is to define the press machine type. As you know, we will use a constant velocity condition. For using that, click on Press, Manual, enter -1 in the fifth column of the table. This means, making the press move downwards, in the negative y direction, with a constant velocity of 1 mm per second. Click OK. The fourth step is to select the friction formulation. Click on Friction, from Library and then select SOAP_cold, steel, click Load and then Close. The properties that were loaded so far will be assigned to the respective entities now. Select the geometry file ending with workpiece.stl, drag it and drop it over the workpiece of stage 1. Select the geometry file ending with upper.stl, drag it and drop it over the upper die of stage 1. Select the geometry file ending with lower.stl, drag it and drop it over the lower die of stage 1. Right-click on the steel grade and select two workpieces. Now right-click on V equals 0, -1, 0, and then select two upper dies. This will assign the press type to the upper die. Similarly, right-click on SOAP_cold, steel, and then select two upper and lower dies. This will assign the friction formulation to the upper and lower dies. Now we have completed the definition and assignment of properties to the dies and the workpiece. The next step is to position the dies properly. For this, we will use the Positioner tool of AFDEX. Double-click on Stage 1 and click on Positioner icon on this toolbar. Click Auto icon. This will enable automatic positioning of the dies. Click OK. Now it's time to define the planes of symmetry. Double-click on SYMM_plane. This opens the Define Symmetry Planes window. Now select the two planes of symmetry in the workpiece. After making sure that the two planes of symmetry are carefully selected, click OK. The next step is to define the stroke. For Stage 1 stroke definition, double-click on Forming 1. This will open the Forming Control window of Stage 1. Select Distance from the drop-down menu next to Stop Criterion and enter a value of 6.2. This is the stop criterion for this stage, meaning that, when the stroke reaches this value, the solver will automatically move on to the next stage. In the case of a 3D simulation, we have to define the nodes between which the stroke value is defined. Click on the three dots next to the distance value that you entered. Now select 2 points, one on the upper die and the other on the lower die, and click OK. The order of selection does not matter. When the distance between these points reaches 6.2 mm, the value that you entered for stroke, the simulation will stop. Click OK. Now the properties of the Stage 1 are all set. We are almost done with the simulation setup process. We just have to save the simulation, check, and run it. Click on the Save icon, enter a file name and then click Save. Your simulation file is now saved. The final step is to check the simulation to see if we have set it up correctly. Click on the tick mark button on the toolbar. In the window that opens, click Check. This will let you know the error messages if there are any. The notice messages can be ignored at this step. After making sure that there are no error messages, click Run. This area shows stage-wise and overall progress of the simulation. On the right side are the different state variables that can be visualized based on the simulation. You can explore more on this section to investigate the state variables of your interest. The media tools here allow you to visualize the deformation behavior of the process.